Spectra analysis. This is a review over what we did during class. I will be breaking up this video into several parts to keep the airtime low. Okay, let's jump into it. We're given a signal, which is in this case, a square wave with no offset, and we're given that the amplitude is 12 volts and tau is 0.5 milliseconds. So tau is half a cycle, and that's 0.5 milliseconds. Now we also are given a low pass filter with gain of 1 with a cutoff frequency of 2 kilohertz. Now we're asked to get the input spectra, the output spectra, and the output waveform. And the tool that we need is the Fourier series expansion for the waveform, which is here. This is what we're using up here. Yes. We have this page, so we use this as a reference. We get our Fourier series expansion ready. Let's start plugging in some numbers. Let's start working this problem. So we know that this is 0.5 milliseconds, and this is the period. So 2 times half a cycle is going to be 1 millisecond, and to find the frequency we calculate 1 over the period. In this case is 1 millisecond, and we have that the frequency is equal to 1 kilohertz. Okay, now this frequency is going to be equal to the fundamental frequency. So we will be using this frequency everywhere. Now let's work on the first harmonic. To find the first harmonic, well, how do we use this first of all? N here is equal to only the odd numbers. So we'll be able to find n harmonics. In this case will be the first harmonic, third harmonic, fifth harmonic, seventh harmonic, and so on. Odd numbers of harmonics. That's the catch for this expansion. And wherever we have an n, we will plug in the harmonics number that we are working with, and wherever we find FO, we're gonna plug in our fundamental frequency. Okay, so to work with the fundamental, which is the first harmonic, we will use the definition, and that's 2 over a n times pi times sine of 2 pi times n times the fundamental frequency times t. And if we plug in our numbers, this will become, well, this is the fundamental sine wave, BF. If we plug in some numbers, the amplitude A is equal to 12 according to our given information, 12. And in this case, because it's the fundamental, the first harmonic is going to be equal to 1. I have to write this somewhere else, over here. So we have 2 times the amplitude, which is 12, n, which is 1 over pi, times sine 2 pi n, which is 1, times the fundamental frequency, which is 1 kilohertz, 1000, times t. So this is what we have, and let's continue working this expression. So we have that the fundamental is equal to 24 over pi times sine 2 pi times 1000 times t. That's it for the fundamental. Now we need to find the amplitude of the sine wave, the exact number. In this case is 24 over pi, which if we use our calculator we can find that quickly. 24 over pi, that's 7.63, 7.64. We can keep it at 7.6 volts, keeping it simple. So this is the first harmonic or fundamental. Let's work with the third harmonic now. Since we're working with the third harmonic and is equal to 3, and we use the same expansion for the third harmonic, is 2 times the amplitude over m times pi, all that times sine 2 pi n for the harmonic number, the fundamental frequency, and t. And also we have here that the fundamental is equal to 1000 and the amplitude equal to 12. So the third harmonic will be equal to 2 times 12 over 3 times pi, because we're replacing n with 3 because we're working with the third harmonic. And all these times sine 2 pi, instead of n we're working with the third harmonic, times the fundamental frequency, which is 1000 times t. Let's clean this up a little. We have 24 over 3 times pi times sine 2 pi of 3000 t. That is our third harmonic, but also we need to find V1. Sorry, V3. The amplitude, the exact number for the third harmonic. And let's factor out 1/3 here and keep 24 over pi. If we do that, this will be equal to 1/3, and we found previously that 24 over pi is equal to 7.6. So for the third harmonic, it will be the amplitude will be 7.6, 1/3 of that, which is equal to, let's use our calculator, let's do this times 1/3, and we have that this is equal to 2.5, for let's round it off to 2.5 volts, third harmonic. Now let's do one more, which is going to be the fifth harmonic. And we can keep going on and on all the way to infinity, but we're not going to do that. We'll work the fifth harmonic. Our amplitude is equal to 12. The fundamental is 1000. And the fifth harmonic will be equal to 2 times the amplitude over n times pi, all that times sine of 2 pi times the harmonic that we're working with, the fundamental frequency, times t. And here let's plug in our data. We have 2 times the amplitude, which is 2 times 12. The fifth harmonic goes here for n, times sine of 2 pi, and the fifth harmonic, which is 5, times the fundamental frequency. Let's clean this up. So we have that the first fifth harmonic will be equal to 24 over 5 times pi times sine of 2 pi times 5000 t, right? 5 times 1000, we got that. So this is our fifth harmonic here. But also we need to find the amplitude, the exact number. And to do that, let's factor out 1/5 out of this picture. So we have 24 over pi. And previously, from the initial computation, we found out that 24 over pi is equal to 7.6. So now we're going to take 1/5 of 7.6. Okay, and this will be equal to 7.6 times 1/5, and that's equal to 1.52 volts, 1.5 volts, 1.5 volts. So V1 is equal to 1.5 volts. Okay, and we're gonna break for this video and start another one in a second.